and sensing joint communication and sensing is probably becoming quite hot topic these days, and probably it's also part of intelligence 6G where the context awareness comes into play. So a bit about my journey in millimeter wave. I don't know it. Yeah. Um, so I did yeah, my PhD in Georgia Tech in mostly on estimation and optimization of layout parasitics for 60 gigahertz circuits, and it was also had quite a bit of machine learning involved, but it was before machine learning was quite cool, so it was just machine learning. So and then I mostly worked on 60 gigahertz product development and system development in different companies. So spent almost 13, 14 years in 60 gigahertz. Okay, why I'm saying this, because 60 gigahertz is still not so widely used. Okay, when we used to talk about it in 2004 or 5, it was like everything will be replaced by 60 gigahertz. But now still 60 gigahertz is used primarily in automotive. The ones who don't know, there's quite a bit of 60 gigahertz being implemented these days inside the car, and also there are a lot of new applications coming up in terms of in the medical domain, right? Because we have good amount of bandwidth available at 60 gigahertz. So what we always think that will happen, that will replace all the HDMI cables by 60 gigahertz, will replace all our, like digital content streaming with 60 gigahertz. That didn't happen as such, but something else is coming out. So that's just a small trailer. I wanted to say that what we are going to talk about today, maybe it will not be implemented that way. It will be implemented some other way. Okay. And then since 2018, I'm part of Barkerson Institute, and finally went a little lower frequencies. Now we work on different frequencies, starting from 5 gigahertz till 77 gigahertz as of today. And a little bit about our institute. We are a nonprofit research institute, and it's fairly new, like not even 7 years now. And we are very well connected to TU Dresden, and primarily a locally funded and third-party project funded institute with 90 plus people. And we started a JCNS symposium 2021, and we are still co-organize the symposium. It happens every year, and we are located in a beautiful city of Dresden. And many people may know Dresden because of a good number of fab being here. But yeah, it's also a beautiful city. You can visit anytime. And our journey so far is that we have close to 15 researchers, engineers working on this topic today out of 90. So it's 1/6 of our strength. And primarily we started with a radar centric view. Then slowly we went to communication centric view, and finally we converge into a giant communication sensing. On many people in 3GPP know it as integrated sensing and communication, ISAC. Okay, and short story in last 5 years, other than the symposium, we also have won several projects, and we started with a metamaterial based project, metamaterial antenna design for JCNS called MetaBoost. And then now we have part of 3 German projects and 2 European projects, apart from being part of some projects like HexaX2, which also I think University of Louis is very, very well involved, and we also collaborate in through our different projects. So with that, I have around 30 to 35 minutes, and first I will a bit talk about, so first of all, it is not so detailed about circuits. I decided to go with a little bit higher level more on the system side, because I think this is a good opportunity for me to talk about what the researchers in JCNS need to do in coming days, right? Because even if you search for a JCNS hardware today, you will find a very limited number of papers, and just presenting our own work and very limited work, I felt it will not be proper justice. So that's why I wanted to talk about more questions than answers, and then how millimeter wave plays a role in that, and then what are the solutions available today, and what should be our goal in coming months, right? And so, yeah, my first disclaimer, it's a very evolving field. So the things that I'm saying today may be less relevant tomorrow. And we are also waiting for a winning applications. So yeah, just to keep that in mind. Second disclaimer is I'm not limiting only to millimeter wave, even if I'm have a huge 60 gigahertz hangover. But from that, I also learned a lesson that finally applications decides how we want to contribute. So if we find applications that uses the frequencies lower than 60 gigahertz or millimeter wave, then also we should use our knowledge. So many things we have done to make a 60 gigahertz product finally being used for something completely different, like uh, even at like if we go for a direct RF implementation, many of the ADCs and DACs that are developed for 60 gigahertz can be directly used now for direct RF kind of applications. Okay, so a little bit of motivation. As we know that continuously the usage is increasing, and the spectrum is not increasing accordingly. So we really have to solve certain challenges, how we share the bandwidth. And the infrastructure is also becoming more and more complex, and scenarios are becoming more and more complex, right? And so we have to be more efficient. There is a lot of bandwidth currently being dedicated to radars, let's say, and at one point this has to be available for communication, or new bandwidths need to be created to support all these efforts. So we have to be more efficient spectrally, and we have to also use hardware efficiently, so that we can support different types of applications. And something basically we can think of can be a killer app in 6G if you have radar as a service. Currently, its communication is a service. Tomorrow, radar becomes a service, and we cannot use them using separate resources. They should share the resources so that it is becomes a like joint communication sensing as a service. And at the same time, there are a lot of requirements where we have to adapt to the environment, and that's where also we really want to bring this to under the same umbrella. Now, a lot of people may say that it's okay. We can work in isolation, and currently we have a radar system, we have a communication system. Take an example of a car. This has also a good amount of communication going around, and also it has a huge number of radars. So it can work as an isolation that is happening today. Cooperation is like can be a little bit of sharing, can be a little bit of information. So it is definitely possible. Even many communication systems and infrastructure can be used for sensing the environment. So this is can be quite near term. But what really for hardware design, hardware people, it is important to do a co-design, right? Because if you actually can do a co-design, you can share the antenna, you can share the hardware, and you can probably convince at one point of time the user that it's just a little bit of extra power or cost, but you have this additional functionality with the joint physical layer and medium access protocol, right? Okay. And for that, we definitely need to work quite a bit on the front end with or without antenna sharing. And this, how you want the co-design, I think we have done several research on that. And we figure out it will be very, very application dependent. So moving along, what can be those applications? So first of all, it's very simple. Traffic where base stations and cars can work together. A classic example is when you are going towards an intersection and a boy or if a human being is crossing the road, then sometimes one car cannot detect it. Then the other can, which is coming towards has the visibility of that situation, can send this information to the other car, or a base station can coordinate all this information. So it can be just for traffic monitoring or road safety. In other words, it can be for 3D map generation. So this is more called environmental awareness, and using that you can actually do a lot of you can increase the efficiency also of, let's say, your current 5G or 6G cellular networks. So to summarize, the use cases can be automotive, context awareness, it can be just environment or crowd monitoring, it can be digital twin, so creating just another digital, so a cyber environment, a copy of a physical environment. AR, VR kind of applications are also thought of right now because you need sensing, right? And you also communicating a lot with a very high data rate. So primarily, it's also a possible application. From a millimeter wave, people, they can also say that we also mostly work in a directive domain. And if you know your receiver location, or at least, for example, when you have a lot of human beings around the transmitter, and through us, the loss is huge, right? A 60 gigahertz channel, we really attenuate the signal a lot. So in such a situation, if you know where are the people, how to send the signal, you can really make it more efficient. And that's why also context awareness plays a big part in directive communication, which is millimeter wave communication. But anything that is suddenly driving all this interest, that's debatable. Okay. However, we know, so the communication is all around, right? So it's in sub-6 gigahertz, centimeter wave, millimeter wave, everywhere. Sensing is primarily at higher frequencies. But we know already that automotive situations, the radars are having a lot of interference. And if you want them to be dependable, you need communication capability. Second, also, if you just use a camera for context awareness, there is a question about privacy and some other issues related to trustworthiness. So a limited capability of sensing can be radar, which usually just knows that there is something, okay? It doesn't know the face of the person. So in such a situation, it can make it more secure. And finally, as I mentioned already, a spectral use can really do a lot of wonders. First, last, sometimes we just do it because we can, because radar is there for like 60, 70 years, the communication systems are there, and many of now slowly communication is moving towards high frequency, and radar is already at high frequency, so why not? We should do that, right? So um, first question then, for hardware development, millimeter wave or not, is which type of radar, which type of communication, right? Because radars, there are some talks about radar yesterday, and also there are radars can be monostatic, where the transmitter and receiver is kind of co-located, bistatic, where they are not, and multistatic, which is a mix of all of them. Second, they use different types of waveform, different type of processing, and if frequency chops is processed primarily in an analog way of mixing, whereas in WaveDM traditional communication waveform is done mostly digitally, right? After demodulation. And then how many antennas, whether you want different types of sensing at the same time. So it's just not one thing, okay? And this is also is important that communication may not mean just high data rate communication for all devices. It can also be energy efficient. Second feature, radars may not mean automotive radars. So we need to think beyond. Just a small background is monostatic radar was on the left. So it's basically mostly transmitter receiver are co-located, bistatic where transmitter receiver are not co-located. Multistatic is a mix of all of them. And you also know that I think this is also an important part where when you are sending something and there is something we want to detect using a radar, there is something very important called radar cross section. Okay, and this radar cross section, if it is too small or it is too stealth, for example, in some military airplanes, then the amount of power that you're receiving is really low. And this goes to the power of 4. If you look at this, let me see if I can get my pointer. Yeah. If you look at this, this is to the power of 4. Okay, which is slightly different than our very well-known communication if you know equation, where it is actually to the power of 2. Okay, the lambda dependence on frequency remains similar, but you have to know that the distance with the distance, the power that is being received for the radar is different, and this is a more or higher order than usual communication. So the bottom line, can we fit everything at the same? If we try to do everything like a 100 gigabits per second, 1 millimeter resolution, joint communication sensing system, it is not. Then let's not discuss it for 6G because it's just 6 or 7 years away, 6G. Okay, we have to follow a step-by-step process. At least I believe. And from trying to find the middle path where we have some application for high performance radar and low performance communication, high performance communication, low performance radar. In some cases, the same communication TRX can be used for radar, and we just find out a small time, but that radar can be a bistatic radar or a monostatic radar. If it is monostatic radar, then we have to think about self-interference. Okay, so I'll talk about those more later, but in the high performance domain, we can also think about make radar coordinated, make communication smarter, so make it more intelligent. Then in the cost efficient consumer domain, we want to enable, let's say, gesture recognition kind of radars. So we want to make it smaller, cheaper, and they're also ubiquitous, means we have communication system everywhere. So that's why we have very cheap communication chipsets. If you have radars in every cell phone, then also it will be cheap. It will not come with a additional cost. And then easily we can make radar as a service, because if it is there everywhere, then you can make it easily a service. Number two question is standardization, and there's also some discussions in the previous talks, but let's me tell you that there are already several discussion about joint communication sensing in standardization bodies, and everybody's talking about it. There is 802.11bf. You should watch out for it because it has something in 5.9 to 7.1, as well as it has something at higher than 45 gigahertz. Okay, and 802.11ad already has is an ISM and 802 and 60 gigahertz, so this can definitely be also used for sensing. UWB sensing is there already being discussed, and 3GPP already there's a study item, so everybody is talking about it. Move forward. Frequency, as I mentioned, traditionally communication is sub 6 gigahertz, or even 5G. There are some bands at 24 to 28, but most of the communication systems today you are basically using is lower frequency. Most of the automotive radars are higher frequency, but there is a sweet spot, and I have highlighted it, which is 60 gigahertz. 60 gigahertz is there in both. And then we have to understand there's a main difference is directive to non-directive, right? So these are the two main differences. And third difference is that communication is mostly not in band full duplex. That means the transmitter and receiver are not working at the same time at the same band, right? But if you think about a regular automotive radar, that's basically TX, and TX is sending signal and receiver is also receiving almost at the same time, with a little bit of delay, and that delay is what people are trying to figure out, right? How different, how distant is the object. And third is mostly communication is baseband processing, which is digital, and radar stretch processing, which is another name of analog mixing. However, there are other type of radars. There are radars which doesn't need to be in band full duplex, like you send a pulse and you receive after some time. So basically, you don't need it to TX and RX to be on at the same time. They just need to switch fast. So there are different types of, but in general, we can say these are the main differences. So now why millimeter wave, right? Um, Millimeter wave has good bandwidth, so radar people will not complain. It is all most of the automotive radars are also directive. So this is the same thing we hear when you talk about 60 GHz communication. It's a line of sight, it's directive, and also it's supports 2 GHz of bandwidth, 2.16 GHz of bandwidth available, right? So that's a good news. Bad news? Yes, of course. Line of sight is also a bad news, and we have to really, somebody has to really analyze why 60 GHz didn't fly as we expected it to be. And we should not repeat the same things for 140 gigahertz or 200 gigahertz, 300 gigahertz. We need to know if 60 gigahertz didn't fly, the higher ones may not fly as well. So we need to understand that. Second, of course, MIMO has MIMO beamforming, anything millimeter wave, we talk about that. We talk about power. I remember some chips have melted because of the beamforming power consumptions. So we have to also understand how we dissipate the power if we really want to go for a very watt solutions, right, for cell phone. So that's why I think these are all the things every researcher needs to think about today, so that this doesn't become a bottleneck tomorrow. Many of them are common, many of them are not common. So we'll talk about that later. But let's summarize. So if you just want to do communication in sub-10 gigahertz, primarily we talk about low bandwidth, but we do a lot of high bits per bandwidth, right? So high bits per hertz, basically. So we are going for higher, more complicated modulation schemes, mostly MIMO. And then millimeter wave, we primarily have a high bandwidth, and of course we can go to 256 QAM or so, but at the same time, maybe sometimes we don't need it. And then we can just make it less power hungry. So, and also we have to compensate the path loss using beamformers. So these are the things we need to understand. These are the main differences. In sensing domain, also there are other types of sensing available, and in when you talk about combining them, we mostly talk about joint communication and radar sensing, right? But at the system level, it can also be have other if you think about automotive as a system, the sensing can be aided by camera, other sensing, and also radar, and finally connected with the communication systems at lower frequencies. So it can be a cooperative system. Whereas millimeter wave has already good amount of backhaul applications, radar applications, and also millimeter wave imaging is there. 110 to 140 gigahertz is being considered. I don't know whether it will be possible at 60 or not, but it has a very good potential. At least some small few gigahertz are already being thought for usage. And also you have 220 gigahertz and above. So the speakers have already presented some of the work at these frequencies. So the good news is that cellular has been following wireless community a bit. I want to, yeah, means in terms of like if you think about this picture, you can go to this paper and but you can always think that it has So wireless community has already showed something, and that has been used in cellular community as well. So 802.11 BF and AD can be something that we start ISAC with or JCNS with, and then that will be followed in 60 cellular communications, right? And then in terms of that, we already have the 60 gigahertz. I really want more usage of this band. It can easily support 10 plus gigabits per second, as well as some millimeter resolutions. Okay, raise the resolution for radar. And if 60 gigahertz becomes successful, I think a 140 gigahertz can follow with higher resolution, lower range, and higher data rate. And I'll not go into details, but these are will be in the slides. So there are already transceiver that have been shown. IMEC has done it, IHP has done it. So, and many companies are also shown results for radar as well as for communications. So you can today buy like from Sivers. I think I'm sure showed a picture from Sivers where you can buy transceivers for communications, and also there have been a good amount of showcase for 140 gigahertz. So they are all available today. So I don't have to worry about that because they are already available. But we need to remember one thing. If we just focus on millimeter wave for JCNS, um, it may become it may become a challenges for certain applications. So we should use practically. We use sub 6 gigahertz when needed. We use 6 to 16 gigahertz if it's being talked about quite a bit nowadays, and that may offer more bandwidth. So we may use it whenever needed. And then we absolutely need millimeter wave, we use millimeter wave. Because path loss is not cheap, you have to compensate for it different ways. Beamforming also sometimes become bottlenecks in terms of power, complexity, and also sometimes with scalability. And that's something we need to keep in mind. And in the picture I'm showing you, because beamforming is a necessity to compensate for the path loss. If you don't do so there is 20, so if you in the TX domain, it's primarily directly 20 log n. In the RX domain, it's 10 log n. But you need these additional things if you really want to extend your like this TX to RX distance. So that's already well known. So if there is a limitation in space, then sometimes we have to share the antennas. But also if you go to higher frequencies, then there is more space to put antennas, right? And sometimes I also know that directive channels can be better for trustworthy communication systems. So there are a lot of good things, a lot of complicated things, challenges, but still we have good. So now what we have today, I'll be primarily, there are a lot of solutions in different domains, starting from physical layer to ADC, DAX. I'm mostly focusing on our analog RF. So as I mentioned, for antenna, the main question one is to ask how much self-interference we can kind of cancel through the antenna domain, in the antenna domain, and how many antennas do we need? And if it is beamformer, how many beamforming? And you think about beamformers, here also you have element to element isolation you need. Same for MIMO. So the techniques we are planning to use for self-interference cancellation in antenna domain, similar things can also be used for element to element cancellation, element to element, like to increase the isolation between elements. And then our main challenge is also that we need to have high isolation, we need to support wide bandwidth, and we need to give high gain. All these things in the same compact package, and that's the main challenge for antenna. For waveform, the challenge is that traditionally radars are all low spectral efficiency, and the communications are all high spectral efficiency. And how come up with something that do justice to both the applications? Now, the third point is how do we actually share the front ends? On the left side, you can see a simple let's say super heterodyne transceiver for communication, where you have your DACs, ADCs, and amplifiers, and multiple LO up conversion and down conversion. Whereas in radar, usually you have a chirp generation, and then it goes through a PA, and then it comes back, and there is an LNA, and after the mixing, it just has a radar ADC. These two ADCs are not the same, because they handle different kind of signals, and also as you can see, the number of blocks are different, and they also have quite a bit of different linearity matching bandwidth requirements. Also, this needs concurrent operation. If you are talking about a regular um, communication transceiver, it's mostly time division duplexing. Okay, whereas this is working at the same time, so it needs to work at the same time. So first solution, let's just go optimize. Let's not think about anything else. Just we first see what are the challenges. Okay, so the contrasting requirement, and also we have to make it low power. On the system, we have to design the transceiver that can support both the waveforms. We need also to support all the multi-chip, multi-pole antenna solutions, and we can have separate radar. So as you can see, so there is one solution that can just say that, okay, fine, great, I just change my the way I'm doing my I add one more receiver, I use the same transmitter, and I use two different modes, one for radar, one for communication, and then I just do have one separate. But this will need more antennas for sure. You cannot use the radar and communication antenna at the same time. The alternative is, if you want to reuse these antennas, then there is also another possibility, where if you can see that this is a standard communication transceiver, and this is a standard radar transceiver, and where in this case we are doing let's say we're doing the generation in a different way. We are using a PLL, and we are basically using a DAC to generate the signal that we want to send. And then you can see that they are becoming almost similar, right? Except this part, where in one case you are feeding the PA back and mixing with it. In this case, you are not doing that, because this is one TX, one RX separate.
Professor Sen, just to remind you, there's about 3 minutes left time. Then we have to then move on. So
Okay, but we have around, I was delayed by
yeah,
15 minutes, right? No?
about it was about 40 minutes per talk. So now we have about, so after 10 past, we should
Okay,
try to
okay,
conclude. Yeah, sorry for
okay,
yes.
okay. Then I will primarily talk about this paper. We have worked on this, and primarily the idea is that we use a switch. And in this case, in one case, it works like a um, communication receiver. In the other case, it's like a radar receiver. In this case, you are switching between either you are using the PLL, or you are using you are using the PLL. During that time, it is working like a communication receiver. When you are feeding back the transmitter, then it's acting like a radar receiver. And some other differences is basically primarily because of the linearity requirements. So the radar needs higher linearities primarily to endure the self-interference. The PA needs to be higher saturated power, and also frequency synthesis needs more wideband, because the radar signals are primarily wider bandwidth. And for IQ, it's not must have for most radar application. And the gap reduces at millimeter wave with fractional bandwidth similar to 3 to 5%. With MIMO radars, like also being popular, and MIMO communication being popular. So when you have a MIMO JCNS, then they all march. So So first enable that I want to conclude is that we need a reconfigurable architecture that can support full duplex communication, half duplex communication, full duplex radar, as well as full duplex, like half duplex radar. Sorry for the, yeah. So, but different types of full duplex radar with different types of processing. That's enabler number one. Enabler number two is a new age 5 that can support different types of signal processing, as well as different types of waveforms. And our enabler number three is full duplex enablement. I have already covered it. So primarily in full duplex enablement, we need to look at, so I will not go into this basics of full duplex. Full duplex primarily mean that you are working at the same time at the same frequency band. And the problem is the self-interference because the TX signal is very high and the receive signal is low. So because of that, uh, the receive signal is sometimes under the transmitted signal that is being kind of leaked. So to avoid that, we have to follow a self-interference cancellation, and that can be done in antenna domain or RF domain or analog domain or digital domain. And that's basically, yeah, I will not go into more details. You can see my slides. They are done in antenna domain differently, and we have done quite a bit of work on that. And but finally, when you look at this picture, this there is a good amount of processing gain, and when you add all of this interference cancellation, and then you have to know that what processing gain can help you recover the signal. And that's why it's important to know the processing gain. It is important to know that full duplex is an enabler for 6G ISAC, and wideband self-interference cancellation is also an enabler. There are many solutions that can do for a very narrow band, but they are not all wideband. So finally, one thing I wanted to mention, so I will finish in 2 minutes. One thing I wanted to mention that right now we really need to do a lot of validation for our hardware, and that's why a self SDR system is a requirement, and that can support high bandwidth for radar as well as complex signal processing for communication, and also has to support all these diverse requirements. And we do that using waveform antenna platforms, MIMO platforms, and front-end platforms. And we have showed one of this demo also in one of our JCNS symposium, where we have used 71 to 76 gigahertz system, and we have used 9 millimeter wave receiver and one combined transmitter and one radar receiver at the same time. And we also, there are AWG, and we have AWG and oscilloscope system that can check up to 25 gigahertz, but this is a very analog way. SDR is more, you can use all the digital platform. So what now? So today we have basically planning to do MAC layer and higher layer updates. Tomorrow we need to do this nearby front ends, and as I mentioned, we have to use this communication TRX for a joint communication and sensing platforms. For example, a TDD TRX for we have a transmitter and receiver, they're working and separately. We just can use as a TDD communication with radar. But for that, we just need to have additional antenna, let's say antenna isolation and some RF isolation to make sure that they work for a radar. Um, Another thing, what we need to figure out is the right application that can also live with lower resolution of radar, and the non-millimeter of the band that can support larger bandwidth. So maybe 6 to 16 gigahertz. For the millimeter wave band, we need to support all the bandwidth requirement, all the beamforming requirement, and finally, we have to go beyond radar. So for the researchers, what we are trying to do now, first of all, there's a lot of focus on self-interference cancellation. Then to enable the beamforming for reconfigurable front end, we are also doing a lot of research on that. Then how we can use the antenna. Finally, if you use 60 gigahertz for 6G, then or like 6G kind of applications, if you can know what kind of the things we need for 7G, maybe 200 gigahertz can be used for 7G. And there's a lot of research going on in reconfigurable intelligent surfaces and how we can embed all of them in the hardware. Finally, hardware co-design is a must for JCNS, and I think just doing things in the physical layer will not help flourish this topic. And that's with that, I will conclude. And thanks for the opportunity. And I also would like to thank all the researchers at our institute. And we also have an opening for a millimeter wave antenna and packaging researcher in this topic. So if somebody is interested here, can also directly contact me at PSN at IEEE. Thank you.
Hmm. Thank you very much, Professor Sen. I think we have to move on. There's one question in the QA. I think you can take that and answer that by typing
Okay.
there.
Okay, I will
And
do that.
thank you for interesting talk. It was very timely topic these days, and it's good that also